everyone. My name is Anqi Fu. I'm a machine learning scientist at H2O. I work on developing and testing distributed statistical learning algorithms. And today I'm going to talk to you about a really cool new algorithm we've developed called generalized low-rank models. It's actually based on a paper written by Madeline Liddell, Corin Horn, Reza Zeta, and Stephen Boyd, who are Stanford researchers. And I did the implementation of this algorithm in H2O. So I encourage you throughout this demo to work through the scripts, the R scripts, which have been given to you as part of the USB stick. It's a very hands-on demo, and you'll get to learn a lot about how to use this as part of a machine learning pipeline. So briefly, I'll talk about what a low-rank model is and mathematically and why you want to use it. So a low-rank model is given that you have a table of data, A. This could be data with mixed numeric, Boolean, or categorical data. It might have some missing values, might be noisy. Regardless, as long as it's a table with M rows and N columns, our low-rank model compresses this data into the two numeric matrices X and Y. So here X, if you look at the diagram, X has the same number of rows as A. So if you have 1 million rows of observations, X will also have 1 million rows. But it'll have only K columns, and K is the rank of the matrix, and it's something a user chooses, which directly correlates to the degree of compression that this algorithm will give you. And Y is a matrix that is K rows, and generally it'll have the same number of columns as A. Depending on how many categories you have in A, it might have larger. It basically summarizes the archetypal features created from the columns of A. So it's a compression of the feature set that you have into a smaller set K. And a single row of X is a row of your data set A, which is an observation, say, in time, but projected into this reduced feature space. You can sort of see the similarities between this and PCA, because in PCA, you have sort of K principal components. And this is sort of analogous to that. In fact, GLRM is a generalized version of PCA, using different loss functions and being able to handle different types of data and data with missing values. So the cool part of it is that you can approximately reconstruct A from the matrix product X and Y. So one advantage here of using low-rank models is that you can actually reduce the storage space. So you can run the GLRM on your dataset A, pick a good K compression parameter, and then just save X and Y. And you can take 10 gigabytes of data and compress it down to 100 megabytes. And whenever you need to reuse A again, you can reconstruct it on the fly from X and Y using the predict function, as we'll see. Given that you've compressed the feature space down to only K, where K might be 10 when you have, say, like 2,000 or 3,000 or 5,000 columns, you can get a significant speed up, as we'll see in many algorithms, because you have less columns and features to go through numeric data. So, for example, in deep learning, as we'll see, we get a 10x speed up just from converting one categorical column and compressing it down using GLRM. We can identify and visualize important features using the Y matrix, as we'll see. These are the archetypes. They present the most important predictors or descriptors in your dataset A. And finally, almost as a bonus, we can impute missing data entries, because when we do this reconstruction here, when we form X times Y and reconstruct A, we get all the missing values in A imputed as well. And this is very powerful because you're not just doing immune imputation, you're not sort of guessing at these missing values. You're using holistically all your data that you have available to you at that point in time to guess at and impute the data that you do not know. And so you get to learn, you get a much more accurate, say, like recommendation engine, or as we'll see, some time series analysis. You get a much more accurate imputation of the missing values. So let's jump into our first example. If you'll take a look at your R scripts, this is the one called walking.gait, our demo walking.gait. And the data set we're going to use is data from a biomechanics laboratory at Stanford. They had a subject walking on a treadmill, and they hooked up some sensors to them, and they have, over time, recorded the location in 3 dimensions, X, Y, and Z, of different body parts. So, for example, the first column is time, the second column here is the X coordinate of their forehead, and then a Y coordinate and Z coordinate, and all the way down to a right toe. This data set A has 151 rows, 124 columns. We're going to build a rank K equals 10 low rank model. And the rows of Y, as we'll see, are going to be a principal stances this person took while walking. And the rows of X will decompose the position that the person has been in at each point in time into these combination of principal stances. So let me pull up R here. Here we go. So initialize, I'll load up my library, initialize H2O, and then here you should have already had the data set path set for you. If not, you would take a look at where that data set is in your path. And we're going to import our Gait data. We're going to take a look at the dimensions. It is, as I said, 151 rows by 124 columns. If we take a summary of it, we see the mean and median and a minimum of each of the locations. And now we're going to run GLRM, and we're going to build a model here. It's going to be on the data set we just imported. We're going to skip the time column because we're only interested in the locations of the body parts. Where compression or rank K is going to be 10. We're going to use quadratic loss, which is generally the default for numeric data. You can use different loss functions depending on how your data is distributed. No regularization, and we're going to run for a maximum of 1,000 iterations. But as we'll see in our plot, it actually converged after only about 14 or so iterations. So this is an iterative algorithm like alternating least squares, and it generally converges much faster than the maximum number of iterations. So let's take a look at our archetypes. We can pull the archetypes directly out of this model object. It's the @model $ archetypes. And we can plot these. And as you'll see, you actually see a picture of a person here when I plot these. So here we go. This is sort of like a person. This is the first stance this person has taken, the first principal stance. This is the top of their head, their right temple, right down to their shoulders. And then in this stance, their left foot is back and their right foot is forward. Now, if we look at the second archetype or second principal stance, we'll see it's generally switched. So here the left foot is forward and right foot is back. And it seems like they're swinging their arms here. And if we go through all our different 10 stances, you'll see this, the person is basically walking in this visual. So each of the principal stances is one particular position their body was in in a majority of the time frame. Now we can look at our X matrix. This matrix we have to actually pull off of the H2O server, so we have to use a special function H.getFrame. That's because X can have, as I mentioned before, millions of rows, so it's not practical to store it in R. But once they pull it in, we can plot it just like any other function. So now this plot is of the archetypes over time. So if we think of each archetype as a stance, then this is periodic, meaning that sometimes the user is in stance 4, say, which is the stance where their right foot's forwards and their left foot's back. And this alternates with the green one, which is stance 3, which is maybe the opposite, where their left foot's forward and their right foot's back. So we actually do expect and see a periodic function here, which describes how the person is walking. Now finally, we can reconstruct our data set A from X and Y, and we'll see if you just use the predict function, you pass in GLRM, this model object we got, and then the original training data set. And we can take a look at the head so we can see its reconstructed data. And once we plot it, we'll see how it compares to our original data set. And it's actually pretty good. So the black line here is the original, and the blue line is the reconstructed. So it follows the ups and downs of this particular body part, which is the left shoulder blade, over time pretty closely. There might have been a little bit error here over at the peaks, and we can actually improve on this by making K larger. So as we make K larger, obviously it's going to be more storage space needed, but you'll also get a more accurate compression. So you're trading off sort of accuracy and how much storage space and time you need to build a model. So the second step, we're going to look at a data set with missing values in it. And it's going to be the same data set, but let's assume that you're a scientist, you're doing this experiment, and your sensor has some malfunction problems. So now you have some missing data, missing entries. You might not know where the forehead is located at a certain point in time, or that data might be noisy. And we're going to actually see how we use GLRM to impute this missing data very accurately. So here I'm going to import this data set. Again, it has the same number of dimensions as before, summary roughly the same, and we have 2,817 missing values, which is about 15% of the data is missing. I'm going to run GLRM again with essentially the same parameters, except for with the missing data as a training frame. I'm actually validating on the data set that I know is correct. This is how you do train validation. Other parameters are essentially the same. K equals 10, no regularization. I let it run for a little longer because I know it takes longer to impute missing values. It needs more iterations to do that. And I found that a different initialization scheme, SVD, actually works better. But you can play with these parameters easily using a grid search algorithm to find the one that works best for you. So let me go ahead and run this. And it will take a little bit longer just to converge. But after convergence, you always want to do this. You always want to plot the model object you get, and you'll see whether or not you converge. So if the plot didn't go down quite enough, then you'll want to raise the maximum number of iterations, or decrease the minimum step size, or play with some of the initialization parameters more until you get a pretty good convergence. But in this case, it works out pretty well. It's converged by around the 1,500 or so, 1,500 iteration. And we know this because we can now impute our data set again using the same function, the predict function. But now we see our imputed data set has no missing values. So almost for free, you get your missing values imputed from the reconstruction. And then once I plot this data set, you can see black again is the original data set that we know is the correct one. Blue is what we imputed, and the little red marks here, which hopefully you can see from the back, they are where we had missing values. So you can see we actually imputed the missing values pretty well down around here, time 1, and around this part. We had some error around this peak at time 2, possibly because there's quite a lot of missing values here, and we might need a little bit more. Oh, and let me just increase the font size since it's a little hard to see. It's a little better. There's no way to zoom this, unfortunately. This is an R. But you can see the red X's over here, and at some of the troughs, there's a little bit more error. But overall, we get a pretty good reconstruction. We can definitely try to do better with K equals 20, say, and doing some more tricks to let it run for 3,000 iterations and get better convergence. So this is the first example, and this is already pretty powerful because you can see how you can compress your data, how you can impute missing values, how you can really visualize and understand what your archetypal features are, your Y rows. So these are not just abstract matrices that you've created. They're actually things you can interpret and use in your other machine learning applications. In our second example, we're going to do something called transfer learning, and specifically what we're going to do is we're going to show how to use GLRM to deal with data sets where you have categorical values with many, many categorical levels. The example here is going to be with zip codes. In the US, there's actually over 32,000 unique zip code tabulation areas, and we are going to look at a data set that has many of these ZCTAs, zip code tabulation areas, and we're going to compress this column such that we can get better predictions faster in deep learning. So the data set we have is from the US Labor Department, the Wage and Hour Division. These are compliance actions against companies who have violated labor laws. The response, or what we want to predict, is whether or not a firm is a repeat and or willful violator. The predictors are going to be the zip code where the company is located, number of violations found, the civil penalties, employees affected, and then various other data on specific laws that were broken. The naive approach in many cases would be to replace the zip codes with indicator variables, but this is very slow because you'd actually be expanding 32,000 potential levels into 32,000 columns, which is terrible and also overfits in algorithms like deep learning. It also can't transfer knowledge between similar zip code regions, so instead of doing this naive approach, we're going to use GLRM. So we're going to have we're going to take another data set, and this is a data set I got from a census, an American Community Survey. This is demographic data by zip code, relating things like the education level, the household, the number of children, the ethnicity of people in this area. We think this will be useful for predicting the violations of companies because we think demographics are going to affect whether or not a company or an industry is going to employ employees, not pay them overtime, or otherwise have violations. So we'll build a GLRM with rank 10. We're going to put some regularization on it to sparsify the features. Rows of Y are going to be our demographic archetypes. Rows of X are going to be a map of these zip codes into combinations of these demographic archetypes. So for example, one row of Y might particularly represent highly educated individuals who are single, who have no children in a New England area. And finally, what we're going to do is we're going to take our training data set. This is our WHD to wage and hour data set, which has zip codes. We're going to take the X matrix from our GLRM, which for each of these zip codes gives us a vector of 10, k equals 10, values that represent them, their demographics. And then we're going to just do a merge here, and we're going to replace each of these zip codes with a unique archetype. So for example, zip code 70525 is going to be replaced here with the row X sub P, so P might be 25 of this X matrix. And so instead of having one large categorical column, we have 10 numeric columns that are dense, and this will actually do much faster and better in deep learning. So let's go right on to the code. Here's the census data set. We're going to go ahead and import our census data. We're going to take out the zip codes because we'll use them later. The dimensions are, as I mentioned, about 32,989, so that's 32,989 unique zip code areas. Now we're going to import our wage and hourly division compliance action information. And give it a bit of time. It has about 208,000 rows and 104 columns. So one of them will be a response. We have 103 columns of predictors. Now, our first step is to run GLRM on our census data. Remember, we're compressing our zip code, so we're running it on our census data. And this will take a bit of time because we said k equals 10. We're going to set some of these parameters here. We're going to standardize it to improve the accuracy. We're going to use quadratic loss, certain types of regularization that I tuned using grid search, and let it run for 100 iterations. So what's interesting and what's really cool here is that once you run this one GLRM, you've compressed, say, census data of zip codes down into these X and Y matrices. You can actually, you don't need to run this again in another application. So say I did this whole model with my wage and hourly data, and now I have some other data set from the US Labor Department that also has zip codes, and I want to condense this one zip code column down. I can just straight out pull my model from memory in H2O and just slap it in and replace that column in that other data set too. So once you build a good GLRM model, you can reuse it again and again. I can, in fact, post this online. You can just try it on your own data set if you have zip code data. So this is finished, and we're going to take a look. And it looks like it converged after 100 iterations, so it's pretty good. Here is the X matrix. These are just the embeddings and archetypes. And we're going to plot a couple of these zip codes. So I plot zip codes like parts of Manhattan, like the Upper East Side and East Harlem, and then parts of California around here, like Sunnyvale and Cupertino. And I expect them to be grouped up by how similar demographics are. So here, I think that's true. McCune, Kansas is a little rural town in the middle of Kansas. It's pretty far out here. East Harlem is a somewhat poorer area with mixed race in Manhattan, which is quite different and far from, say, Cupertino and Sunnyvale and the Upper East Side, which are all sort of grouped together here, down here, because they're very similar demographics. And then these are far away from our rural area. So these, if that reminds you of something, it probably reminds you of principal components analysis. And it's because GLRM is actually, if you run GLRM with quadratic loss and no regularization on a purely numeric data set with no missing values, you can actually recover the PCA, principal components. So there's actually a parameter you can use in there. You can look in the help files for that. So now that we've done this, I'm going to take a look at our archetypes, and I'm going to do a performance comparison. So my first step is just to do a straight-out original data set. Didn't modify categoricals at all. We're going to do a 80-20 train test split, and we're going to run it and see how long it takes to run this prediction with deep learning. Remember, we're predicting whether or not a firm is going to be a repeat and/or willful violator using all of the predictors that we have in our wage and hourly division data set. So as you can see already, it's taking quite a bit of time to even start up because it needs to handle this categorical column of zip codes. And once it starts up, it's going to take a bit of time to finish. And at the very end, we'll compare these three different paradigms. So this one is running. It's going to hang for a bit at the end as it tries to collate our information together. Our next step after this will be actually to take and merge in some of our information. The X matrix, remember from our slides, what we're doing right now is we're going to do this step where we take X, slap it in, replace the ZCTAs here, and get this matrix. So we can do that with a simple left merge operation, which is supported in H2O here. We're left merge WHD and ZCTA. Now we run this again with deep learning, and you'll see it starts and runs much faster. So here it is. It's going, and oh, look at that. It's already done. So that was amazing. And just for comparison purposes, I thought, well, what if we didn't bother using GLRM? We're just going to take all our census data, all 150 columns, and just slap it in and replace the zip codes in our WHD data. You know, maybe that'll do better. It might take a little longer, but who knows? And we're going to take a look and do that here. So we'll do another merge and run deep learning again. And we expect this to take a bit longer because instead of having 10 columns of condensed demographic data, we have 150 columns of dispersed demographic data. And then finally, we look at our performance comparisons. Let me pull this up and zoom in a little. Or maybe I'll zoom out here. Here we go. So our original data set, which is not modified at all, it took us about 40 seconds on my very fast Mac laptop. It got a training or a test log loss error about 0.19. With the data set that had the reduced columns, so rather than having the categorical zip codes, I had the 10, k equals 10 merged in X matrix for my GLRM. It took only 5 seconds. So I've already sped things up a huge amount. And I've actually achieved better log loss error here. I only have 0.18 log loss error. The reason is, as we've looked at, is because of overfitting. The way that deep learning handles categoricals and how things like GLM handle categoricals is not very optimal when you do the one-hot encoding. So rather than doing that, you would actually prefer to use GLRM to condense that data in some way. And then finally, with our combined data, it takes a bit longer here, 6.54 seconds, and it also doesn't do as well as my reduced data set. So overall, we see that using GLRM in this process leads to significantly faster runtime, less storage space, and oftentimes even better accuracy because you've sidestepped many of these overfitting problems and you've used transfer learning to improve your knowledge of particular categorical levels. So that's the end of my presentation. If you want more of the mathematics, there's the paper, the slide. This is a link to the paper online by Madeline Odell and Stephen Boyd. And Madeline Odell is actually giving a talk on day 3 of H2O World Conference at this very room. So you can come to her talk, and she'll go into more of the mathematical details and more applications of GLRM. The examples are given to you in your USB sticks, and the data set is online. So I'm happy to take some questions.
Yeah, I was just wondering how sensitive are these to the parameters I use them? Because I tried the same thing, for example, in the Python implementation, and I didn't get anywhere near the same clustering of the cities.
It will actually be different because if you don't set a seed, there's going to be some randomness in initialization. Generally, it should do pretty well, even which particular example was an issue?
It's the same one, but in my example, for the Upper East Side and East Harlem are clustered with Sunnyvale, and then Cupertino is down, Salt Lake City is up.
Oh, yeah. Okay, so in this example, yes, this plot will actually change somewhat depending on how you initialize things. So I set a seed. If you want to have a better plot, you should set k equals 2, and you get a 2-dimensional plot. The reason is that I have 10 different dimensions. I've only plotted on the first 2. So even though East Harlem and Sunnyvale are close on the first 2 dimensions, they're likely very far apart on the last 8 dimensions. But we don't see that because we only have a 2-dimensional representation. If we set it to be k equals 2, we get all the differences compressed into these 2 dimensions, and we have a much better plot. I can actually run that, and you get to see a curve here, basically.
Is there some kind of guarantee that the first 2 dimensions that you pick, regardless of the seed, are always representing the same thing, or is it possible that they were actually mixed up?
No, there's not a scree plot like a PCA, so all dimensions are of equal importance. They just, represent different differences. So some demographic terms might be compressed in the first dimension, like, number of children or household size, and some things like ethnicity will be compressed in different dimensions.
Thank you.
Yeah, I would like to know if this is randomness dependable. I'm here. If there is any limit on randomness dependency, meaning what's the guarantee that any matrix can be decomposed in, two lower upper matrix decomposition?
You can decompose any matrix that has numeric, categorical, or Boolean data, including missing values, into X and Y. Depending on initialization method, you might get a different decomposition each time. You can set a seed to get the same one over and over. The reason is because the way you initialize it matters. So I use SVD or K-means plus as one initialization scheme. And then it does a iterative optimization algorithm where it minimizes it over time. Generally, it will perform pretty well with K-means or SVD decomposition. And what you're really interested in is the reconstruction error, as we showed in the first data set where I had the little red X's. So if the reconstruction error is very good, as in very small, then the decomposition doesn't matter significantly, I think, in terms of your use case. Because you can have different X's and Y's. It's non-unique, basically, the X and Y decomposition.
I have two questions. The first one is PCA is more sensitive to normalization, so do you have to do with GLRM too?
You generally want to standardize, yes. So I have this transform equals standardize here, which is a parameter that you can set. It'll automatically standardize your input data and then run the algorithm.
And you mentioned there is a similarity between PCA and K-means. At least that's what the paper said. Can you maybe dive a little bit detail on that?
So I think that there's two things. One is that we initialize the X and Y matrices of the algorithm using K-means plus. So the algorithm starts with X0 and Y0, and these are determined by some initialization scheme like K-means plus. And then we go from there and iterate and get a best X and Y fit. The second thing is that you can actually reproduce K-means using specific regularization functions, which are outside the scope of this talk, but Madeline will go into them. If you enforce a certain scheme on structure on X, for example, if each row of X can only have 1 and the rest are zeros, and then Y has a certain structure, then you can actually recreate the clusters of K-means in Y. And then X will be the assignments of your data set into the Y K-means clusters. So that's actually described in the paper that Madeline has.
Okay. One last question. So in PCA, you use sometimes elbow method to do the find the best value for K. Would you do that same on GLRM?
I didn't quite catch the first part. What method?
The elbow to get the right value of K, to get the optimum
value.
Oh,
you mean the scree plot?
Yeah.
In this case, no, we don't have a scree plot for GLRM. So the way you choose the best parameter is you do a train validation where you actually take a data set where you know all the values in it, or most of the values in it, and you deliberately randomly seed missing values into it to create a training set. So now your validation is the known values. The training set is the data set you had with seeded missing values. And then the error is a reconstruction error, which is produced actually in the model. So from the model, I think I had here Gait.glrm2. I'll print out here the reported on validation error, what the error was. And you can take a look at that, and you try to minimize that, because that shows how well you've minimize the error of the reconstruction on your missing values that you've seeded.
Hi, can you say something about the challenges in implementing this algorithm?
Yes, there were many challenges actually, particularly initialization schemes. So we were looking at ways to deal with initialization with data sets that had very very wide columns, which obviously you would want to use GLRM in. And at first SVD, the singular value decomposition, the standard way of doing that was you taking a gram matrix and trying to do SVD on that, but that was not a great way to do it because you already have a lot of columns. So instead we used a new experimental method that basically projects the original data set down to a random smaller subspace and then does an iterative algorithm to get the approximate SVD. So that was one challenge. Other challenges are more computational. So we often had times where we had to run GLRM over and over. We didn't want to initialize the algorithm over and over because actually if you do initialization with k-means++, that can itself take quite a long time. So we put in a model caching framework where if you initialized GLRM already in the past using certain parameters, we'll automatically pull those initialization x's and y's right out of the memory and use those automatically without having to reinitialize. And then other challenges that I'm working on now in our roadmap are doing offsets and scaling for non-numeric data sets. So that's coming up, and that's a bit of a challenge, especially with categoricals, being able to do optimization problems on each column.
Do we have any other questions? We've got time for a few more if anybody has any other questions about it. Yeah, and actually I remember in the early toy data sets, the time was all being consumed, the majority of the time was being consumed by the initialization stuff. So, all right, well, so if we don't have any more questions, we have a break now. We'll have a panel here at 4. I think it's building smart applications. And so we've got, refreshments and stuff outside, and I'll see you guys back here at 4. Thanks.